Okay, welcome back. This is paper 4, variant 2, May, June 2017. Okay, it's question 2A, first of all 2A is about transformations, which did not come up in the June 2018 exam, paper 2, so I'm assuming there will be something about transformations that does come up in the paper 4. Okay, so I decided to do this question. Now, in this question, part A, part 1 says translate triangle T after the translation by vector 6 minus 5. Okay, so what we've got to do is we've got to make sure that everything moves 6 spaces to the right and 5 spaces down. Okay, the vector 6 minus 5, so we've got 6 minus 5. It means you go 6 to the right and 5 down, okay? So every point in this triangle must move like that. Now, before you start moving, check the scale. If it's 1 square per unit, you have nothing to worry about, okay? So you can just move by the squares, okay? Whereas if sometimes you've got like, that might be 1, that might be 2, that might be 3. It'd be 2 squares by unit. You go by the number of units, not the number of squares, okay? So in this case, there's no problem. There's 1 square, 1 unit. You don't have to worry. Now, what I will do here is I will take the right angle, okay, which is this corner here, the corner with the right angle, and I will translate that 6 spaces to the right. So you start at 2, going to end up at 8, and then 5 spaces down, so it starts at 10, it's going to go down to 5. So that corner is going to end up at this position here, okay, which is 8, 5. You see, it's gone 6 spaces from 2 to 8, and it's gone 5 spaces down from 10 to 5, okay? So that point has now been translated. Okay, 6 units to the right and 5 down. And then I don't have to do the same for every other point. I can just say, okay, I know that this point here is exactly 2 squares to the right of the corner, so that's going to be over here. And I know that this point here is exactly 6 spaces below the right angle, so this is going to be down, 4 spaces below it. 1, 2, 3, 4. So it's going to be 4 spaces below it, so it's going to be here at 8, 1. Okay, so you've pinpointed all the corners, and you can just join them together with straight lines, and you've drawn your triangle. Okay, so that's the answer for part A, part 1. Okay, it didn't tell you to label it, so what I would do, just to make it very clear for the examiner, is that that's my answer to A, part 1. Okay, so that's very clear. Sometimes they say label it with a different letter here. They didn't say anything. I just said draw the triangle T. Alright, the image of triangle T, so that's going to be A, part 1. I'll just put it there so that he knows which part refers to what. Then it says the triangle T after rotation through 90 degrees anti-clockwise with center 410. Now what I would suggest you do here is you use a piece of tracing paper, which I will get from. Okay, so here's a piece of tracing paper which I prepared earlier, and I'm going to place a piece of tracing paper over the triangle, and I'm going to trace over, okay, this is what I've done already, trace over the triangle on the tracing paper. Then I put the pin at the center of rotation. There's the center of rotation. Okay, it says triangle T after rotation through 90 degrees anti-clockwise about the center 410. Okay, so the center is 410, so it's a rotation. It's a rotation. Let me just put this back here. Alright, so it's a rotation, and the center is 410. Okay, and it's anti-clockwise. Anti-clockwise. Alright, so the center is 410. Let's see where 410 is exactly. 410 is right here. 410. Okay, where I put the point. Okay, so the point that this corner of the triangle is the center of rotation. Okay, so we see that already. Okay, so right now, okay, so I'm going to put the pin of the pencil on the center of rotation, and then what we'll do is we'll rotate the shape around 90 degrees anti-clockwise. Anti-clockwise, remember clockwise is this way, anti-clockwise is the opposite direction. Anti-clockwise is the opposite way from where a clock turns. So this is how your shape is going to end up looking. It's going to look exactly like that. That's when it goes. That's where it's going to end up. 90 degrees anti-clockwise. You see, I've gone through 90 degrees. Yeah. That's exactly 90 degrees. So we can see where we end up. We end up in this position here. Okay, so we've got basically this point here, this point here, and that point there. Okay, so you move your tracing paper away and you join those points together. Alright, so that's a rotation of 90 degrees anti-clockwise. Okay, so that's A part 2 done. So that's the answer to, whoops, that's the answer to A part 2. That's A part 2. Okay, that's part. Now we go on to part 3, triangle T after enlargement with scale factor half, center 10, 0. Okay, so you're going to do scale factor of half, center 10, 0. Okay, the center is 10, 0. 10, 0 means 10 on the x-axis and 0 on the y-axis. So 10, 0 is exactly over here. So this is the center of enlargement. Okay, 10, 0. That's the center of enlargement. I'll just mark it with an E. Okay, and we got to find the triangle T after the enlargement scale factor half. So we got scale factor half. So we got an enlargement. So it's enlargement. Scale factor half. Center is 10, 0. So as I always said, I like to use vectors for something like this. So I'm going to pinpoint one of the points. For example, let me use a right angle again, using vectors. So I'll say, okay, how do I get from the center of enlargement to where it is right now? Well, I've got to go -8 and +10. So to get me from the center of enlargement to this point over here, okay, I've got to go 8 spaces to the left and 10 spaces upwards. So -8 and +10 will take me to this corner there, and I know that I need to multiply that by the scale factor, which is +1/2, as you can see, right? So if I multiply this vector by +1/2, we're going to get -4 and 5. -4 and 5 from where? From the center of enlargement. So -4 is going to take me to 6, and +5 will take me to this point here. See? So I can see that that is where the right angle has been transformed to. Okay, the right angle has been moved from there to there. Okay? Now, the rest of it you can do without actually using vectors, because you can just use a scale factor. You know that every length is going to be half of what it was in the original shape, because the scale factor is a half. Okay, that's like the length factor. So if that's 2 units long, on this point it's going to be 1 unit long. And if that's 4 units long, on this it's going to be 2 units long. The length is going to be half as much. And then you can join those together. See, that's like 2, 4, that's 1, 2. So everything's a half of what it was, and there's the answer to part, I think it's A part 3? A part 3. That's the translation, and that's A part 3 here. A part 1, 2, 3. ... Okay. Just about see that. So there we have our 3 transformations that they gave us. There was a translation, a rotation, and an enlargement. Okay. Okay, there's other ways to do this, especially the enlargement. I always like using vectors, but it gives precise kind of positions rather than drawing lines across. This gives precise kind of positions. So I like using vectors, and you only need to transform one point, and the other points you know where they're going to be because of the scale factor. Okay, and if you're ever confused, if the scale factor is a bit strange, you can just do the vectors for all 3 points. Okay, so there we have our the first part. Part B I'll do now because it's a very short little question. Just make some more space here. Describe fully the single transformation that is represented by this matrix. Okay, so now some people actually memorize these, matrices. I hate memorizing things, okay, especially things like this. Certain things are good to memorize, but sometimes when you can understand and not have to memorize, then it's better. So for example here, I would call this I, and I'd call this J. This is one way of doing it. It's called unit base vector. So I is always on the x-axis at 1, 0. J is always on the y-axis at 0, 1. That's how you always start. Okay? If they're asking you what this matrix does, particular transformation matrix does, what transformation does it cause? Okay, what you've got to know is the first column is the new position of I, the second column is the new position of J. So I'm going to plot 0, minus 1, 0, minus 1, which is over here. That's called I dash. That's where I has moved to. And then minus 1, 0, minus 1, 0, which is over there. That's where J has moved to. And I've got to think to myself, what is the transformation that takes J to J dash and I to I dash, both at the same time? That single transformation that will take both of them to that. So if I said, for example, rotation of 90 degrees clockwise, that would work for I, but it won't work for J, because J is going in the opposite direction. And you can't have two different transformations, one single transformation that will transform, that matrix causes, okay? So I've got to think what actually does both move J to that point and I to that point, and we can see quite clearly it's going to be a reflection in a line that's going to go diagonally across like this. Okay, if you reflect in that line, then this will move to there, and this will move to there, okay? So that's the reflection, and this line, okay, which passes to the origin, and it has a gradient of -1, so y equals minus x. So you can say this is a reflection, in the line, so just write in, reflection in y is equal to -x. Okay, and there we have this question fully answered. That's question number 2 from that paper, summer 2017, paper 4, variant 2. Thank you very much for listening, and keep your eyes peeled for the next video. Thank you very much.